So now we're going to look at another example of doing statistical analysis with non-interval or ratio data. And in this case, it's about ways that students got to a nearby event called Foxfield, which is a horse racing event that students go to annually. And our question is, did each year of student use the same types of transportation to get to Foxfield? And we have actual data from this from a few years back. This is some of the actual data. 4 different years of students and 5 different ways of getting to Foxfield, either a chartered bus, a CTS bus, which is a university bus, they drove a car, they rode in a car, or they took a taxi. So we want you to pause the video now, and you can go to the Excel file. The actual data is there, and figure out what kind of analysis you would run it, and see if you can answer this question. Alright, so hopefully you've had a chance to try to run this analysis and see if the 4 different years have taken the same types of transportation to Foxfield. Now, another way of wording this might be is the distribution of types of transportation taken the same for each of the 4 years? That sounds clunkier, but that's going to clue you in that this is a chi-square analysis. We want to see if essentially the same percentage of first year, second year, third years, and fourth years took each of the 5 types of transportation. So let's go get the data, which is in Excel, the raw data, and then take it to, in my case, Minitab. We're going to go under Stat, and then Tables, and then there'll be options for doing chi-square. In our case, we have data that's raw data. So I'm going to use the rows field to be the year, and the transportation type to be the columns. And then I'm going to go in and I'm going to make sure that it's doing a chi-square analysis, and that it's storing the expected cell counts. I find those useful, and the standardized residuals, which are useful. And that's enough, and we'll hit go. Alright, so here are the results have spit out. I'm going to go back to PowerPoint, see all these results up here, because I have these in PowerPoint, and they're a little bit easier to see there. So our overall result is here. Our p-value is 0.069. So if we're being strict about a 0.05 alpha value of being significant, we would say this isn't significant. But it's really close. I mean, it appears as though between these 2 different ways of calculating chi-square, the Pearson chi-square and the likelihood ratio chi-square, these are pretty close to this 0.05 value. It looks like there might be some differences, some slight differences in the ways that different years of students get to Foxfield. And to figure out that in a little more depth, we'll look at this larger table of contingency results. So in this larger table, we see that 5 different types of ways of getting to Foxfield. 1 is each column, and the 4 different years, 1, 2, 3, 4. And then we're going to see the actual values. It shows each of these cells has the count, then the expected count, then the standardized residual. The count, the expected count, the standardized residual. And the standardized residual, the larger it is, nominally over around 1.96 for our z-value, those are going to be the most significant differences of the group. So we know that we're right around the 0.05 value for our p statistic, just a little bit over it. So some of these are likely going to have standardized residuals at or near just over 1.96. And if we look, we see in particular that third years appear to have something going on with how many of them rode in a car or a truck or a van. And it looks like their actual count of 85 is a lot higher than their expected count of about 67.9. So more third years rode in cars and trucks and vans than would be expected, is how you would interpret that result. And looking around, none of the other standardized residuals are particularly large. Maybe the one here, negative 1.6, is getting kind of large. But the biggest one clear is this one we already have highlighted. Now there are some assumptions of chi-square The data needs to be independent, which you could check in this case if the data were listed in the order it was collected. We're not going to check it. Each of these categories needs to be mutually exclusive or independent from each other. So like for each person, there's only one value in this table that represents that person. So there's one third year who drove a car in the study. And then the one we really want to focus on is that cell counts need to be greater than 5. And we can quickly see that we have problems here. We have the one I just pointed out, the third years that drove the car. First years that drove a car as being fewer than 5 people have done each of those. So what can we do about these cells in violation of our assumption of chi-square? This is where a lot of common sense comes in. One is maybe there's a way for us to collect more data, and we actually get enough data so all of our cell counts are greater than 5. In this case, let's say that's not a possibility. So what else could we do? Well, it looks like if we just took out the driving car option, that it's so infrequent that maybe we just remove that one completely and do the analysis of the other 4 types of driving. And note that we're not including driving yourself as part of our analysis. Or we look at it the other way and we could kind of split it into upperclassmen and underclassmen, so combined first and second years and combined third and fourth years. Clearly we're losing something there, some of the richness of our data, but on the other hand, we're meeting the assumptions better. And if we think that upperclassmen and lowerclassmen, underclassmen is a fair way to group students, then that could be a way to run our analysis. So sometimes it's grouping things together that you'll do in order to help get enough counts in each cell above 5. Other cases, you might need to delete one of your levels because it's just not happening enough. And in other cases, if you have a chance, you might collect more data.